In this video, I want to take a look at Taylor series. Now, Taylor series are a way of taking a known function and writing it as a power series. Here's how we do it. Suppose I've got a function f of x. Now, it has to be a kind of a special function because it needs to have infinitely many derivatives at some given value of x called x0, right? And then we can write f as a power series like this way. Before we do, though, let me point out that there's a lot of functions that we deal with that have this property. Polynomials have infinitely many derivatives. Most of them are zero. E to the x, any exponential function, trig functions, combinations of those things. There's just a bunch of functions that we deal with that have derivatives and continue to have derivatives as you keep taking them. Okay. So the function, I need to know the function value at x0, I need to know the derivative of x0, I need to know the second derivative at x0, I need to know the third derivative of x0, and so on. Now the first part of this actually should look vaguely familiar to you because you had Calc 1. And this first part is the linear approximation to the function at x0. F of x0 plus f prime of x0 times x minus x0, that's the linear approximation. What we then do is we add on this quadratic piece, which those together would be the quadratic approximation of the function. And then you add on a cubic one, and so on. So the total is what's called the Taylor series, and it is equal to the function f of x, at least within the interval of convergence of this power series. And shorthand way of writing this, the sum from 0 to infinity of the nth derivative of f prime of x. I'm going to fix that because we generally write the nth derivative in parentheses there so it doesn't look like f raised to the n power, that somehow we differentiate that. Differentiate the derivative? Yeah. So anyway, the nth derivative at x0 divided by n factorial times x minus x0 to the n, right? That is the Taylor series. Now, in the event that x0 happens to be 0, then this is just an x to the n, and that's sometimes called the Maclaurin series. Maclaurin series is just a special case of the Taylor series. In fact, I want to do an example here and generate the Maclaurin series for e to the x, that is the Taylor series at x equals x0. So the function's e to the x, and my center point is at x0. I need to know the function at 0, it's 1. Then I take the derivative, and then I need to know the function of that at 0, it's also 1. You know, e to the x is maybe a little boring in its derivatives because all the derivatives are the same, they're all e to the x. So the nth derivative at 0 is going to be 1. And so when I plug a 1 in for this and that and that and that and that, and zeros in for x0, I get this right here, that e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. We saw this in an earlier video when I was talking about complex numbers and used a bit of this to explain why e to the I x is cos x plus I sine x, and I used this Taylor series or Maclaurin series for e to the x. I also used sine x and cosine x, so let's take a look at those. Here's sine x. Again, I'll do it at x equals 0. So f of 0, sine of 0 is 0. The derivative of sine x is cosine x. Plug a 0 and you get cosine of 0 is 1. Take the next derivative, it's minus sine x. So the second derivative is 0 at 0. Third derivative is minus cosine x, which gives you a minus 1 when you plug a 0 in. Fourth derivative is back to sine x, which gets me back to 0, and then perhaps you can see that this will repeat itself. I get a 0, 1, 0, minus 1, 0, 1, 0, minus 1, so it keeps wrapping around between those four values. So when I plug that all in, there's the 0, and there's the 1 times x to the first, there's the 0 divided by 2 x squared, and the minus 1 divided by 3 factorial x cubed, and so on. And the Maclaurin series, the Taylor series for sine x, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7 over 7 factorial. Man, that is not written right. Let's see if we can fix that. That looks better. X minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus and so on. The later in the day it gets, the harder it seems to me to be able to edit my own work here and see the mistakes before I get to the point of trying to record. Anyway, written as a summation here, it's a little trickier to do just because those zeros take out every other term. So the way that I'm doing this here is I'm using 2n plus 1 instead of n in places. So when n equals 0, 2n plus 1 is 1, right? And the alternating sign comes from the minus 1 to the n, because minus 1 to an even power would be 1, and minus 1 to an odd power would be minus 1. So starting off here at n equals 0, this is going to give me a positive, and the 2n plus 1, 2 times 0 plus 1 is 1, so that gives me that x. Then plugging in n equals 1, this will be a negative. This is a 3 factorial in the denominator, and this is an x cubed, and so that's this term, so on. Okay. So the Taylor series for sine, or the Maclaurin series for sine, is this right here. Likewise, we could do the same thing with the derivatives of cosine and plug it in and get this. 1 minus x squared over 2 plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. There's a couple things here that occur to me that I should say. 2 is, of course, 2 factorial because it's 2 times 1, right? And 1 factorial is 1, and 0 factorial is also 1. That's by definition. So every place we ever seem to need 0 factorial, it needs to equal 1. So that's just definition. 0 factorial is equal to 1. Okay. A couple things to notice here that I find interesting. Sine is an odd function, right? The symmetry is about the origin. If you plug an x and a minus x in, you get opposite results. And the Taylor series for sine is all odd powers of x. Likewise, cosine is an even function. You plug in a positive x and a negative x, you get the same result. So that is symmetric about the y-axis. And when you look at the Taylor polynomial for cosine, it has all even powers of x, which each is symmetric about the y-axis. Okay. There's one more I want to do here, and that is this 1 over 1 minus x. And I want to do the Maclaurin series, so I want to do the Taylor series at x equals 0. Okay. Now, I could take derivatives of this, but I'm not going to. I'm actually going to come up with this a different way. I'm going to do it with polynomial long division. And let's see if I can switch over to this other thing. Okay, so I want to take 1 minus x and divide it into 1. Okay. Typically when we do polynomial long division, we do it with the polynomials written in descending order of power here. So, but when we're doing division of power series, we write them in the other order, as it turns out. So I'm going to do, how many times does 1 go into 1? It goes in 1 time. So 1 minus x, and then I subtract. So change that to a minus and that to a plus and add. So the 1's cancel out and I get an x right here. 1 minus x goes in, 1 goes into x, x times. So multiply, I get x minus x squared, and subtract. So change the signs and add. Those go away and I've got an x squared. Now the 1 goes into the x squared times plus x squared. So this would be x squared minus x cubed. Change the signs and add. I got an x cubed here. And perhaps you can see that this would continue forever, and that the result is 1 plus x squared plus x cubed plus. This is a geometric series with c equal to 1 and r equal to x. And so this power series is equal to 1 over 1 minus x. Notice that the interval of convergence here should be from -1 to +1. And I can see that in this process of long division as well, because where is my, there we go. Because the remainder here, that is, you can do all sorts of crazy things with long division as long as the remainder is getting smaller each time. Then you're not going astray. If the remainder is getting bigger each time, then your answer is getting further and further away from what the actual answer should be, right? But if x is somewhere between -1 and +1, I keep getting bigger and bigger powers of x as I go down here. But for x is less than 1, or in between -1 and +1, raising to a bigger power means you're getting smaller and smaller results. So the remainder is getting less each time, and we are getting the appropriate answer here. So the power series for 1 minus 1 over x is 1 plus x squared plus x cubed plus x to the fourth. I had a student a few years ago who referred to this as the Ice Cream Theorem. So there's your brief introduction to Taylor series.